Welcome. My name is Jord Warmink. I'm from the University of Twente. Thank you for being here and thank you for the possibility to present this paper. This work was mainly carried out by Mark Frankena as his master thesis and Vera van Bergwijk in close cooperation with Paul van Steeg from Deltares. The title of this talk is Quantifying the Influence of Transitions on Grass Cover Erosion by Overtopping Waves. A strong grass cover is essential for reliable flood defense that are subject to wave action. When waves overtop the dike, the overtopping water rushes over the crest and down the landward slope, leading to erosion of the grass cover layer. The left picture shows an experiment with the wave overtopping simulator that are typically used to simulate overtopping waves to determine the strength of grass covers. Here you can see a continuous grass cover. But in this talk we focus on transitions in the grass covers, because these transitions are known to be weak spots. However, how much the strength is reduced at these transitions is still unknown. With this study, which is part of Vera's PhD work, we aim to quantify the strength of these transitions. Dike covers are generally not smooth profiles but consist of different materials and geometries. Any change in dike cover material, height or angle is called a transition. These transitions affect the strength because the continuous grass cover is interrupted, but they also affect the wave overtopping flow. In the top left you can see a sketch of a dike profile where the transitions are indicated. A transition from a road to grass affects the flow because there is a difference in roughness. Also, the inclination points from the crest to the slope and from the slope to the toe or to the berm are transitions that cause additional turbulence, which then affects the flow downstream of the transition. The top right, you can see an image of a dike in the Netherlands, where a lot of these transitions are present. In this research, we only focus on the transitions indicated in green, from the slope to the toe or from the slope to the berm. At these transitions, additional turbulence is generated, which means that it has an effect on the flow downstream. In this study, we use two models, the hydrodynamic erosion model and the cumulative overtopping method. The cumulative overtopping method is currently the standard model used for strength analysis in the Netherlands and is developed by Jens van der Meer and his co-workers. The final models are shown at the bottom of the slide, but to explain them, I'll walk you through their different components. Start at 1. Both of these models assume that erosion occurs if the depth average maximum velocity of a wave is larger than a critical velocity, which is called UC in the COM or UT in the HEM. The difference is that the HEM computes the velocity varying along the entire slope, while the COM uses a characteristic velocity for every section of the slope or berm. Step 2, we add the influence factor for the load. Both methods have an influence factor, which is called omega for the HEM and alpha m for the COM method. These influence factors express, for example, the additional turbulence that is generated at a transition. Step 3 and 4 are less important for this study, but they show the influence factor that affects the strength of the dike cover. In step 5, both of these models sum up the damage of all the overtopping waves that occurred during a storm. The difference is that the HEM computes the erosion depth along the whole profile, and the COM method gives a damage number to express the damage of the dike cover. The most important part here is that both models have an influence factor that express the additional load due to transitions indicated by the green circles at the bottom. We only looked at one type of transition, the transitions from slope to toe or slope to berm. Both models were applied for 7 wave overtopping simulator tests, and what we did is we calibrated these influence factors. All the other strength parameters were constant and were not varied. The procedure was as follows. First, A critical velocity for damage in the model was calibrated by comparing the wave overtopping tests for a location without a berm. And then we give this calibrated critical velocity. We use that to compute the influence factor. Here at the top, or this scheme, what you see here shows the results for the HEM model, and here at the top you see the calibration where we compared the mean erosion depth with the measured erosion depth to get the critical velocity, and at the bottom for the location with a transition we compared again the mean modeled erosion depth with the measured erosion depth, and based on that comparison we calibrated in this case the R0 value, which is the influence factor for transition. Here you see the same approach, but then for the COM model. The difference is that for the HEM we use the observed erosion depth, while for the COM method we use the observed damage category. Furthermore, the procedures for the COM and for the HEM were the same. Here you can see again the approach that we use for the landward toe of the dike transition, but it's also applicable for a slope or a berm transition. So for the HEM we compared the erosion depth, we determined the minimum critical velocity, and then we calibrated the influence factor, and for the COM we used the damage number, we determined the minimum critical flow velocity, which is a characteristic of the slope, and then we calibrated the influence factor for the COM method. This figure illustrates the calibration approach for 2 out of the 7 experiments, T2 and T4. The dotted horizontal line shows the observed erosion depth for both tests, while the solid line with the dot shows the modeled erosion depth using different values of the turbulence intensity parameter. At the locations where the lines cross the calibrated turbulence parameter, we see then the optimal calibrated value. Both of these tests resulted in a calibrated value of 0.45 for the turbulence influence factor. So, although the observed damage for these two tests was different, the calibrated influence factor was the same with a value of 0.45. I can tell you that this was not the case for all the experiments. The influence factors for the COM method were derived in a similar way. This figure shows the calibrated influence factors for all 7 experiments. You can see the experiments in the top row. For HEM, the turbulence intensity ranged between 0.2 and 0.45, while the influence factor for the COM varied between 1 and 1.8. Please note that for the afsluitdijk 1 case, both the HEM and the COM result in a small value of the influence factor. Here you can see the same results in a graph. Vertical you see the calibrated load factor, and horizontally shows the different tests. The X values here show the theoretical load factors derived by Hofmans. This figure shows that in general steep slopes have a high load factors compared to mild slopes, and that all calibrated load factors are higher than based on theory, except for the afsluitdijk 1 case. Similarly, here you see the results for the hydrodynamic erosion model. In the vertical, again, the calibrated turbulence factors, and horizontally the 7 different tests. Also, this figure shows that in steep slopes we have higher influence factors, and for the turbulence intensity no theoretical approach exists, so there are no x's to compare. What we can conclude from these results is that the turbulence intensity for HEM, or the load factor for COM, is not a constant, but it depends on, amongst others, the upstream slope. Therefore, there is a need to derive, to look at new formulations for turbulence, as turbulence is one of the key processes that explain the erosion at transitions. One other observation that I would like to share is that we carried out this study for a range of different overtopping volumes. This figure shows with the different colors the different average overtopping discharges that were done in the tests. Even though the significant wave heights were slightly different in these tests, in general a higher overtopping discharge means that more large waves, and therefore we have higher flow velocities on the slope. We noticed that for higher overtopping volumes, the calibrated values of the turbulence decreased, which implies that more of the erosion depth is explained by the flow velocity and turbulence is relatively less important. That brings me to the conclusions about this research. We wanted to quantify the influence of transitions on grass cover erosion by overtopping waves. So the first question was, what are representative values for these turbulence parameters? So the results show that for mild slopes, in general, we can say the influence factor had a value of 0.25, and for steep slopes 0.45. And for the cumulative overtopping method, the load factor, alpha m, varied between 1.3 and 1.6 for mild slopes and 1.5 to 1.8 for steep slopes. So finally, we have shown here a method to analyze the influence of transitions on the erosion of grass covers to quantify values for the influence factors. We also have some recommendations. As in this study, the values of CE, which is a strength parameter for grass and clay, were kept constant. Also, the strength of the grass cover was fully defined by the critical flow velocity. Therefore, further research to determine values for the CE parameter for both grass and clay is needed. Also, the COM method cannot yet deal with the damage after a grass cover is removed. So we also recommend to determine values for a damage number for clay without grass. Finally, we only studied here one transitions, but many more types of transitions exist for which the influence factors still need to be determined. And with that, I would like to thank you all for watching, and I hope to see you in Sydney in 2 years. Thank you.